Hi, I am Arijit Chatterjee from IISER Pune. I'm a fourth year PhD student. Thanks very much for the organizers to allow me to speak to you here. So today I'm going to speak to you about the dynamics under superposition of unitary operators. We have realized this in our lab. I'm an experimentalist, and our investigation of temporal correlations under these special maps. This is our recent work. It's done in collaboration with Dr. Karthik and Professor Usha Devi and Professor T.S. Mahesh, who's my thesis supervisor. Okay, so what a superposition of unitaries, right? So we have heard about superposition of states. If you take two quantum states which are physically distinct, for example, a cat is dead or cat 1 and a cat is alive or cat 0, and quantum theory allows the cat to be in a superposition of this dead and alive state. So this is well known. But what about superposition of unitaries? So if we consider two unitaries on a qubit, for example, simple rotation of the block vector represented in the block sphere, one rotation about x-axis and the other rotation about an axis phi, which makes an angle phi with the x-axis, and this phi is going to be crucial later on. So if you put phi to be 0, then u0 and u1 are the same. And so now if you increase phi, then u0, u1 starts differing. So it somehow captures how distinct these two unitaries are. But now what do you mean by superposition of them? So we understand superposition of states. So let's use it here. You add an ancilla to your system that interacts to the system with this Hamiltonian, so that the total unitary through which the system ancilla system propagates looks like that. And now you can read off what is happening. So if condition to the ancilla state, when the ancilla state is 0, system passes through unitary u0, and when the ancilla state is 1, the system passes through unitary u1. And now you could ask that, what do I mean by superposition of the unitaries? Well, you put the ancilla in a superposition state between 0 and 1, right? So that's exactly our strategy is. So let's, the ancilla in a superposition between 0 and 1 with superposition parameter alpha. You could see that if alpha is 0 or pi, it means no superposition, and alpha pi equals pi by 4, you will hit the maximum superposition. Now the system rests in a product state with this ancilla state, and now you just allow your system to interact with the ancilla up to time tf, and this is how the final state would look like. And now you can see that if I measure the ancilla at this time, and if my outcome is let's say 0, then my system have passed through unitary u0, and if the outcome is 1, then my system has passed through unitary u1, and in between the system was sort of passing through both unitaries, and the marginal evolution is non-unitary, so the question through which unitary it was passing before I measure ancilla carries no meaning, likewise in the state case. So this is a very basic realization of superposition of unitaries. It doesn't do much. So can we make it a little more interesting? That's the question. And keep the same setting, okay? You add the ancilla at t0, let it interact up to the time tf, but instead of measuring the ancilla in 0-1 basis now, let's measure it in the coherent basis, in the plus-minus basis. And what happens then at tf? So a little bit of algebra shows that the final state takes this form. The system subspace is not normalized. We just divide and multiply with the normalization factor, which, by the way, this is also crucial, depends on the time interval tf minus t0. So the final state has this structure. So the final state has this structure, and now you could see that now if you measure the system, let me show it here. Now if you measure the ancilla and you get the outcome to be plus, your system has effectively passed through this unitary, which is u plus, and if you get the outcome to be minus, then your system has passed through this unitary. Now these are non-trivial unitary maps. So why is that? Because first of all, look at this normalization factor that is sitting in the denominator, which depends on the interval, and you take the square root of that and divide it. So these unitaries has nonlinear dependence on the interval. So they have very non-trivial nonlinear temporal features, and that makes them not to obey the product law as well. So just to give you some sense of flavor of this nonlinearity, you could see that the effect of these unitaries, if you keep t0 fixed and continuously increase tf, then their effect on the system state is like this, so it provides a very nonlinear evolution to the system. This particular case is for phi equals 90 degree at maximum superposition of 45 degree. And it gets even more, interesting actually. It's just not. I'm very sorry, it's just not changing. Okay. So if you now keep the same superposition, and if you just increase the angle between the axis of rotation between, so you make U0 and U1 more distinct now, and you see that it gets even more bizarrely nonlinear. So this is, if you pick the initial state of the system to be 0, then under U plus, the system almost stays in the 0 state, and once in a while, it makes a very quick rotation. And similarly to the state 1, so U minus, it causes the state 0 to come to state 1 and stays there almost for eternity, and once in a while it is making a rotation. So two states are very highly localized in 0 and 1 respectively. And the experimental realization of this is also, as I said, very simple. So all you have to do, if you want to realize this between time t0 and tf, you take the system, you add the ancilla prepared in the superposition state at time t0, let it interact with the system up to time tf with the Hamiltonian h, that depends on phi, so that gives you control over phi, and then at the final time you just measure the ancilla in plus minus basis, and if you get the outcome plus, you have effectively realized this U plus map. And if the outcome is U minus, you have effectively realized U minus map. So that's the experimental realization. Now you could ask that, okay, you have realized these maps, which looks very non-trivial in the lab, but what have you investigated? Because they have very non-trivial temporal feature, a natural thing to investigate is temporal correlations. So we have done that with the help of Leggett-Gerg inequality, which is the sort of the temporal versions of what Bell's inequality is for the spatial correlations. So let's take a two-level system and a dichotomous observable Q. That just means that the outcome could be +1 or -1. And you think of measuring that observable on the system as the system evolves in time. So you measure it at 3 different time instants, let's say T1, T2, and T3. And every time you're going to get these outcomes +1 or -1. So let's say you measure it at T1, get +1 or -1, you note it, measure it at T2, you note the outcome, multiply them, and you get a number which is either +1 or -1. Do that for many times and just take the average of that outcome. So you'll get a number between -1 and +1, and that going to be the 2-point correlation function between T1, T2, name it C1, 2. Similarly, you can experimentally measure the 2-point correlation C1, 3 and C2, 3. Now what Leggett-Gerg inequality tells you is this particular linear combination, I'm so sorry. So this particular linear combination of the 2-point correlation functions, C12 plus C23 minus C13 should always be less than equals to 1. And the derivation is very similar to the derivation of Bell's inequality. You assume some minimum assumption of classicality, and that allows you to derive this inequality. I'm not going to get into the details of those assumptions here. But the key thing is now if you experimentally violate this inequality, then you certify some quantum feature of your device. So certainly it becomes an experimental test to certify quantumness. And there are initial experiments done on superconducting qubits, and this was done in NMR from our group years back, which now which violates experimental violation of Leggett-Gerg inequality to certify the quantumness of those experimental setup. Now, you can see in all of them, you are violating LGI, you are going above 1, but seems like you are being restricted up to 1.5. You are not being able to go beyond that particular number when you are doing the test on a qubit evolving under a unitary transformation. But if you think of it a while, these numbers, just purely algebraically if you think, all of these can take value +1 or -1. So algebraically this could be +1, this could be +1, this could be -1. So algebraically the maximum value it could hit is +3. But as you could see that seems like even quantum theory restricts the value of this LGI up to 1.5. This started to become known as the temporal Chelsea bound in comparison with the special Chilson's bound for the Bell's inequality. But then the question is now, of course, can we go beyond it with the help of our these unitaries, superposition of unitaries? So that's the experiment that we did, and it's a very interesting setup. So and very simple setup. So you prepared your qubit. We have prepared our qubit in the maximally mixed state. That will be the state on which we are going to do this testing. And let's say I want to measure the correlator C12. So I measured the system, the sigma z, we choose to be the observable. And also we have chosen the time interval to be same. So T1, let's say, is 0, then T2 is T, and T3 is 2T. So they're equally separated for now. That's the experimental setup. And now let's say I want to measure C12. So I add so after measuring the sigma z at T1, you add the ancilla. So so you add the ancilla prepared in the superposition state of alpha superposition parameter, remember. Let it interact up to the time T2, and then measure. So let's say you want to examine Leggett-Gerg inequality under the map U plus. You could also do that under U minus as well. So you at the end you measure the ancilla in plus minus basis and keep those experiments on record whenever you hit plus, and you throw away the minus results. So whenever you are hitting plus, you have effectively realized this unitary transformation U plus. And then again you measure sigma z, multiply the outcome, repeat the experiment. That gives you the 2-point correlator here, C12. And similarly, you can get C23 and C13. So what are the results of this experiment now? So first we set alpha equals 0. That's the normal case of no superposition. And if there is no superposition, then you could see that you are hitting 1.5. So that confirms the presence of temporal Chilson's bound here. Now if you make the this is for phi equals 90 degree. And now if you make the superposition to be maximum at 45 degree, then you see a clear violation of temporal Chilson's bound because the error bar is lying above that. And that is showing that by doing superposition between unitary, you could actually violate the temporal Chilson's bound. Now what happens, because even at the maximum superposition, if I make U0 and U1 more distinct, then we have seen some bizarre, even more nonlinear features of these particular unitary maps. So why not to test it here? So so you increase phi to 135 degree, and you see as expected, the violation gets even more gross. And if you increase phi to 160 degree, you could almost see within the experimental limitation that LGI is hitting its almost algebraic maximum plus 3. So that's a very clear and convincing experimental violation of temporal Chilson's bound for a qubit evolving under this superposition of unitary maps. Now that's the main result, but one more thing, because I think I have some time. So let me tell you. Yeah. So okay, so this is very nice, but we all experimentalists deal with this problem that okay, you are certifying some quantum feature, but if you allow your system to be there for a long time, then eventually decoherence will come in and it will push your quantum system to the classicality. So how this particular feature signatures into the Leggett-Gerg experiments, it's signatures like this. You start increasing the t, the time interval, and you will see that which was above 1 initially, eventually it will fall below 1, and that will actually demonstrate that the system has in some sense classicalized due to decoherence. What happens if this is for simple unitary, the zero superposition, do the same thing for the superposed unitaries, and this is what you will have. So first of all, if you keep the same, so if you make the superposition to be 90 degree, you see that the system is now violating LGI and thereby retaining its quantum feature for some bit longer time. And now if you increase phi, so if you make U0 and U1 even more distinct, then you will get an enhancement of the quantum lifetime for a strikingly even more longer time. And these are the numerical these are the numerical results that we found, that you could get up to 4 times extension of the quantum lifetime due to this superposition of unitaries. Okay, so but before concluding, because I have, I think, 1.5 minutes of time, let me give you a 1 minute experimentalist's understanding to how to understand what is happening. Okay, so this is a bit heuristic, but it's a very picturesque understanding. So first thing, why we are getting these violations. Okay, I hope this is working. Yeah. So notice that this specially constructed unitary maps, they are nonlinear in the time interval tf minus t0, but then nonetheless they depend on this particular structure tf minus t0, and which makes them time translational symmetrical. So so that means that in the Leggettgurk experiment, C1, 2 and C2, 3 are same. So the K3 parameters takes this simple form here, and now just look at this formula and intuitively ask, how can I hit the maximum? So to hit the maximum, you need C12 to reach 1 and C13 to hit -1. That's the way K3 will hit +3, right? Now imagine in the Heisenberg picture, you have taken sigma z as the observable, and as sigma z rotates under the unitary, from T1 to T2, the angle it makes, the cosine of that angle will give you this 2-point correlator. So what you are practically actually demanding is for, in the Heisenberg picture, sigma z to almost not to rotate between the time interval 0 to t, and then suddenly rotate 180 degree between the time interval 0 to 2t. So you are demanding this kind of a nonlinearity, and now if you visualize this, I'm almost done. This is exactly what is doing, right? It's almost staying still between 0 to t, and it's making a sudden rotation which captures this. So this temporal feature is having its imprint on the Leggettgurk inequality and giving you the violation. And again, the enhancement or the robustness against dephasing noise, dephasing is maximum in this region, in the Bloch sphere, and it is almost has no effect in the poles. But because in the Heisenberg picture, it's very easier to think, the sigma z is spending most of the time near the poles and passing through the equator rather quickly, that is actually giving you the robustness that you are getting. Yeah, so that's all the results. So this is currently on archive, and thank you very much.
Thank you, Arijit. Questions? Yeah, so can someone please pass the mic here?
Thanks for the very nice talk. I have a question. You mentioned that there are some experimental data points.
Yeah, these are experiments, yeah.
So what was the experiment? How did you do the experiment?
In NMR, liquid state NMR.
Aha, okay, thanks. And you did the experiment and the theory yourself, or?
Yeah, so theory was done in collaboration with our collaborator, Dr. Karthik and Professor Usha Devi, and experiment part was done in our lab.
I see, yeah. Thank you.
Yeah, Parveen and then Prabha.
So in the beginning, you mentioned that depending on the post-measurement state of the ancilla, you get some U plus or U minus. What happens if you average over ancilla outcomes?
Yeah, so no, this is to realize U plus and U minus. If you average over means that if you don't post-select, you are saying.
Yeah.
Then the system will pass through sort of a quantum channel, which is the probability of getting plus outcome times U plus, probability of getting minus outcome times U minus.
Yeah, and how does that dynamics look like? Like the
so
average dynamics?
That will be simply the statistical average of these two, as which I just showed, the Bloch sphere. You take the statistical average of that.
You don't have that average evolution here?
Here in the slide, no.
Okay, thank you.
Hi, it's more a comment than a question. So there is this whole quantum switch framework and causal switch and all that by Chiribella and so on. And this your initial framework reminded me very much of this switch. Yes. So are they two related?
So in the quantum switch, you have two unitaries, U1, U2, and the game there is to find the commutator or the anti-commutator with a single shot measurement, which you cannot do without this formalism. So similarly, you put an ancilla, you let it interact, And there, if the ancilla out comes plus, then you get the commutator, and if the ancilla out comes minus, you get the anti-commutator. And there also, this is in that sense similar formalism. You let it interact, and then you measure the ancilla to get the outcome.
Okay, got it. Yeah, thanks.
Any other questions? So Arijit, I have a question, or rather observation, if you just look at the dynamics of the two quantum states that you had on they really look like relaxation oscillators.
Sorry? Yeah, the localized in the 0 and 1 state. And
no, but if you look at, van der Pol oscillators and things, very typical dynamics of relaxation oscillators, they have a slow direction and a fast direction.
Yes.
And this looks exactly like that, right? There is just, around the poles, they're very slow, but then once they get off the poles, they become very fast.
Yeah.
This can't be without exciting things. Like, this can't be
with only one.
I think this is an interesting observation. Let me just say it,
And only one difference is there. Let me just point it out, that in that case, you have, whenever you have a time dependent equation in a dynamical equation, you break the time translation symmetry there. But here it's just saying that initially, let's say I want to measure from T2 to T3, from T1 to T2 nothing is happening because the initial state is identity. At T2 it starts there, and at T3 it is doing the same, and the same thing is happening between T1 to T2. So that's an external added point that allows us to go even more, even beyond it, but yeah, we can discuss this.
Any other questions? Otherwise, let's thank Arijit, but also the other speakers. So this brings us to the conclusion for today.